So when we talk about web performance, we are not referring to a single monolithic concept. Instead, it's a complex tapestry. It has multiple aspects and metrics that we can categorize under three broader types. First, we have load performance, which refers to how quickly resources of a page can be loaded and displayed to the user. This is crucial because the faster your page loads, the quicker users can interact with it. Secondly, there is runtime performance. A well-optimized runtime performance ensures your page remains responsive and effective over time after it has loaded. This includes things like JavaScript execution speed, memory usage, and event handling. And the third piece of the puzzle is render performance. It focuses on how smoothly your page can render and refreshes, especially during interactions like scrolling and animation. In real-world scenarios, you'd usually want to optimize across all three types for the best user experience. Having explored the three pillars of web performance, let's turn our attention to rendering. So what exactly is this process? At its core, rendering is the process of taking your code, the HTML, JavaScript, and CSS you have written, and turning it into something the user can see, interact with, and experience. This journey begins with parsing your HTML and CSS code in order to understand the structure and styling instructions, and also the behavior defined by JavaScript. Then the browser will construct the document object model, or DOM, which is a tree-like structure of your HTML. Then come layout, where the browser calculates where each element should be positioned and how much space it should occupy. And finally, the browser paints. It fills in pixels according to the layout it computed, bringing your page to life. Let's see now a visualization of this process on Mozilla Firefox. We will see the work done by the browser in order to show us this page, which has a header, a subheader, some elements in the middle, a footer, and some items on it. This demo is actually extracted from Ryan Saddon GSConf Talk 2015. So here you can see how the browser is figuring out where each element and its children should be positioned after converting the DOM nodes into render objects with visual output and graphic info. If you would like to create such a visualization by yourself, you can go to Chrome DevTools, like I'm doing here, and click on the three dots, then click on More Tools, then Rendering. On the Rendering panel, you can choose Paint Flashing in order to highlight areas on the page with the green color that need to be repainted. And you can also select Layer Borders to show layer borders with the orange olive color. Then you can refresh your current page or call the URL you want to. Here I'm refreshing the medium.com page. And now I will go to my profile page and check its rendering and loading process. So here I'm repeating the same scenario, but a bit slower. So depending on how much time the browser will need to load and display the content, the user may notice the following steps. First, the navigation will begin. Then the first non-blank paint will be noticed on the screen. After that, we have an important metric, which is first contentful paint, and it reflects that the navigation has successfully started. After that, the page's primary content will be visible. Then the page will look nearly done. And then we have another important metric, which is time to interactive. It means that the page or the content is visually usable and engageable. And this will bring us to the end of load lifecycle. This journey has 3 key moments, which are whether something is happening on the page, whether the page is useful, and whether it is usable. So now that we have a better understanding of what rendering is, let's shift our focus to how this process can take place. Not all rendering is created equal, and different methods can have significant impacts on performance and user experience. First, we have server-side rendering, which means that the HTML is fully rendered on the server and sent to the client. In the Angular realm, SSR is based on Angular Universal, a technology that allows Angular to render apps on the server. By default, Angular renders apps only on the browser. With SSR or server-side rendering, apps render on the browser faster because the user can start seeing the page while the rest of the JavaScript is still loading, which improves the perceived load time. With this approach, there is no need to powerful client devices because most of the heavy lifting is done on the server. And it's also SEO friendly. Yet, SSR can put a heavy load on the server because each request will need a fully page to render. SSR can also delay the time to interactive because you may notice the page or see it quickly, but you can't interact with it until all the JavaScript is loaded and executed. SSR may also not work well with apps that manipulate the DOM. As second approach, we have CSR, or client-side rendering, in which the browser downloads the JavaScript and then uses it to create and insert HTML into the DOM. With this approach, all the logic, data fetching, templating, and routing are handled on the client rather than the server, which is actually great for apps that need rich interactive features. Interactions are much smoother because no round trip is needed to the server for each change. CSR also reduces the server load. The server is mostly responsible for the initial payload and for handling the API calls. You can also cache data and states on the client without involving the server. Yet, with CSR, you may have a slower initial load time because the browser or the client will need to load, parse, and execute JavaScript before it can start rendering the page. Search engine crawlers might also struggle with or don't fully understand CSR pages, though some search engines have optimized their approaches to crawl and index CSR pages. And of course, powerful client devices are more required and recommended with CSR applications. But that's not the end of the story, because there is a third approach that seeks to combine both benefits of CSR and SSR, providing us the best of both worlds. A page can use SSR for the initial page load to improve the perceived performance and SEO, then switch to CSR for subsequent navigation and interaction. As symptom of poor rendering, you may notice long time to interactive, sluggish responsiveness, and layout shifts. Layout shifts occurs when elements on the page moves around unexpectedly. Here we have a demo of such a case. Here the user is on the order confirmation page. They see that they have 56 items and they need to confirm this and place the order or go back. In our case, the user wants to click on no go back, but as they try to do so, this element is displayed on the page, which looks like an advertisement, which led to the rest of the page to move to the bottom, and the click event was triggered on yes, place my order instead of no go back. So the user is frustrated. They try to click on no go back, but without an effect. And such a scenario could have major consequences depending on the specific case. I'm going to show you how to measure layout shifts in web applications with Chrome DevTools. To do so, you need to open Chrome DevTools, then go to the Performance panel, and there you can choose this memory select box and click on the garbage collection button. After that, you can start recording, then call the page that you want to investigate. So here I am going to perform a short scenario. I'm going to click on an article, and then I'm going to click on a tab here. Let's stop recording the performance timeline record and wait a bit till the performance timeline record will be generated by Chrome DevTools. This could take a few seconds or much more long seconds depending on whether you have a lot of tabs opened on your browser and so on. So now I have my record. Let's select this section, for example, and investigate it in more details. And here, as you can see, in this row, I see this lila rectangle, which refers to a layout shift in the application. When I select it, I can get more details about it. Here I can see that the appropriate DOM element associated with this layout shift has moved from this location to this location, and from this location to this one. And that's it. And the culprit behind this could be inefficient JavaScript or CSS, large DOM blocks, unoptimized images and media, too many HTTP requests, lack of caching, server performance, excessive use of web fonts, render blocking resources. Render blocking resources are files that prevent the browser from displaying a web page before they are fully downloaded, parsed, and executed. As optimization technique, you can reduce your JavaScript execution time. You can also optimize your CSS and images. You can also minimize layout thrashing. Layout thrashing occurs when JavaScript repeatedly changes the DOM and forces the browser to recalculate layouts and elements' position and dimensions, which can cause a poor rendering performance. In the following example, the browser will need to recalculate layout after each write operation because the next read operation might be affected by the previous write. And this can lead to poor rendering, as I have mentioned, choppy animations, and laggy user experience. If you are working with Angular, you can also leverage on-push change detection, but keep in mind that the on-push change detection cannot be used out of the box. You need to consider your code design and take care or try to avoid mutabilities issues. You can also leverage progressive rendering and lazy loading because they improve the perceived performance and they reduce their initial payload and the time to interactive. That's it for today. If you liked the video, don't forget to hit the like button and subscribe to the channel. And see you next time.